I'm going to give a quick walkthrough using this common emitter amplifier to show amplifier terms that we use for analyzing them for small signals. All right, so we have this common emitter amplifier here. We have our power supply. This is all symbolic for now. We have a input voltage source, a Thevenin equivalent output impedance. Now it's just represented as a resistor, but it could be a generic impedance, complex value. We have an input capacitor. Its role is to separate the DC solution from our input signal. We have our amplifier core here, just a single transistor amplifier. We see that the signal comes in on the base and it exits on the collector. That makes it a common emitter amplifier. We also have this C out. This separates the DC portion that is at the collector just to get this transistor in active mode, and that signal is passed to the output. We're going to call both of these capacitors BFCs. Big fat capacitors. That means that they are a short circuit at any frequency of interest. Right? So we look at that. That's going to be short circuit. What I want to do is draw a box around my input. That's my signal source. This is not part of my circuit. Of course, it's part of my circuit if I have an input, and we have an amplifier. Of course, we have an input. Capacitor, is it part of it? That's up for a little discussion. Also, we have the output. It's a bit pointless to have an amplifier but not connect it to anything. We call that the load. And it's just represented by a resistor here. It could be some other complex valued impedance. Finally, we have the amplifier itself, what we would draw a triangle around. Because this RS is not part of my amplifier, I'm going to take my source, look into my amplifier. So this signal source looks in and it sees stuff. Same thing. I see that this gets represented with a voltage source with output resistance, Thevenin equivalent, and that's what drives the load. That's all I need to know about this amplifier. All right, so what I did is I took this circuit and I made the small signal model of it. I'm also declaring that this emitter capacitor is a big fat capacitor, and it looks like a short circuit at all frequencies. Not always true. It depends on how it compares to this big RE. What it looks like. I have my two resistors, R1 and R2. R1 rotated here, parallel. R2, our AC equivalent circuit. RC goes from the collector, what now turns out to be the AC0. I'm going to do this and put a parenthesis AC, so it looks like an AC0. The 0 not because it's on the top, but because this voltage source turned into a short circuit, because it's independent. And then I took my transistor. Here's the base terminal, here's the emitter terminal, and here's the collector terminal. Replace that with the small signal. I'm going to draw a box around my source again. Pen here. And then my load. What's inside is the amplifier. If I look at the input resistance or input impedance of this amplifier, these two terminals are my input port. Looking in this direction, draw kind of an arrow like that, and I'm going to say R in, that's input resistance of the amplifier. Same thing over here. My output terminals are here. Remember that capacitor is short circuit. I'm going to draw an arrow looking to the left. Call that R out. V out divided by V in is the gain of this amplifier. We'll see what that is here in a second. Okay, if I look, what's the resistance looking to the right? This boundary here, I look here, it's R1 in parallel with R2. Section, this is parallel with R5, so R in is 1, parallel R2, parallel R5, that's great. R out, I'm going to find the resistance looking to the left. I see RC in parallel with RO, parallel with whatever this thing is. Remember, when we find equivalent resistances, we set our independent sources to 0. This is an independent source, and I'm going to set it to 0. Circuit, 0. This, you can analyze that this voltage at the base node is 0. That means VBE, little VBE, the small signal version, across the base emitter is also 0. One more step, VBE is equal to 0 times GM. I don't care what GM is at this moment. This is 0, a current source that looks, with a value of 0 always, looks like an open circuit. We're just left with R out is RC in parallel with RO. Make sure you get your capitalization correct. Yes. All right. We're going to look at this. What is V out? Well, I'm going to keep these three terms separate. You'll see me keeping those in here. But I just do KCL at this. So I'm going to at the top. So KCL at the output node. Two names for these. And I get GM, VBE goes out, plus, and I'm going to write these all together. The current that goes out of here is V out divided by RO parallel RC parallel R, that parallel combination. All of that current going out equals 0. Let's figure out what VBE is. You look up, find here, VBE is always the voltage across R pi. VBE is the same as VN. Hey, this is great. So this is just VN. A little bit of manipulation here, and I can get out left side equals minus GM VBE minus GM V, I'm going to call it in, times rho D our load, parentheses here so we don't forget, our gain, which is defined as V out over V in, is simply move V in over the other side, minus GM, RO, RC, R load, and that's it. Call this a V. I have my input resistance, my output resistance, my voltage gain. And that's it. That's all I need to know. What I can do is I can, if I need the Thevenin equivalent voltage gain, remember that the Thevenin equivalent voltages are with a open circuit load. So if I take off our load, I just end up with minus GM RO RC, but not in parallel with our load. So I'll call this AV0 is minus GM RO parallel RC, and that's it. Let's draw this one more time. This is how I view this amplifier. I have my original signal source with an output resistance, a Thevenin equivalent output resistance, S for source. Okay. I have input terminals to my amplifier. I have an input resistance, Rin. This is right here, Vin. Then I have a voltage source that is dependent. Thevenin equivalent to be A, V0, Vin. Turns out these are connected. We'll keep them connected. Have to be for other sorts of amplifiers. This is R out. Output terminals. And then finally my load. What are we left with? Well, I have. I'm going to point this out, keep pointing this out. This is a model of my source. This is a model of what I attach things to. Call it the load. And in between here, my amplifier. If I can make this find R in, R out, and AV0, Thevenin equivalents, then I can go ahead and write down, give the information that I need.